Segment 1. Our journey begins beneath the crust, in the raw embrace of the earth itself. Forget online retailers and sleek packaging, we are going primal. The first instruction is to locate deposits rich in silicon dioxide, the fundamental building block of the transistors that will form our computer's brain. This won't be easy. You'll need geological maps, a sturdy shovel, and the patience of a mountain. Look for quartz veins, often shimmering white against darker rock. Once found, carefully extract chunks of the raw material. We are not looking for polished crystals, but rather the unrefined essence from which our digital world will be forged. Remember safety, wear gloves and eye protection. The earth yields its treasures grudgingly. Segment 2. Next, we seek the conductive heart of our machine, copper. This reddish-brown metal, vital for carrying electrical signals, lies often in sulfide ores. Explore areas known for volcanic activity or sedimentary rock formations. You might find veins or disseminated deposits. The extraction process will likely involve more strenuous effort, perhaps requiring a pickaxe and chisel to break through the surrounding rock. Collect sufficient quantities. We will need it for wiring and circuit board traces. Again, respect the power of the earth, secure your work area and be mindful of loose debris. Our computer's nervous system is taking its first, crude form. Segment 3. Our quest for elements continues with aluminum, prized for its lightweight conductivity and structural properties. Bauxite, or a reddish-brown rock, is our target. It's often found in tropical and subtropical regions that have experienced extensive weathering. Look for layered deposits near the surface. Extraction might involve digging and sifting. Collect enough to fashion the computer's chassis and heat sinks. Remember to document your findings. Note the location and type of ore. This geological record will be a testament to the fundamental nature of our creation. Segment 4. Now, for the rare earth elements, crucial for the magnets in our hard drive and speakers. Neodymium, dysprosium, and others are often found together in deposits associated with igneous rocks or placer deposits accumulations in riverbeds. This will be a more delicate and potentially challenging endeavor. You might need specialized tools for separation later. Collect samples carefully, labeling each distinct type of ore. These elements, though small in quantity, are vital for the functionality of our digital device. Segment 5. With the raw materials gathered, the arduous process of refinement begins. Our silicon dioxide needs to be purified to an almost unimaginable degree. This involves crushing the quartz, followed by chemical treatments to remove impurities. Hydrochloric acid and other potent chemicals will be necessary. Exercise extreme caution, wearing appropriate protective gear and working in a well-ventilated area. The goal is to obtain nearly pure silicon crystals, the foundation upon which our transistors will be built. Segment 6. The copper ore must be smelted to extract the pure metal. This involves heating the ore to high temperatures in a furnace, often with the addition of other materials to facilitate the separation of copper from sulfur and other impurities. This is a demanding and potentially dangerous process, requiring careful temperature control and ventilation. The molten copper will then need to be cast into ingots for later use. Our conductive pathways are starting to take shape, born from the heat of the earth. Segment 7. Refining bauxite into pure aluminum involves the Bayer process, a chemical method that uses sodium hydroxide to dissolve aluminum oxides. This process yields alumina, which is then electrolytically reduced to pure aluminum metal through the Hall-Héroult process. This requires significant electrical energy. Consider harnessing a natural source like a nearby river to generate the necessary power, further grounding our creation in the environment. Segment 8. Separating the rare earth elements from their ores is a complex chemical undertaking, often involving solvent extraction or ion exchange techniques. This requires specialized knowledge and equipment. Consult geological and chemical texts for detailed procedures. Carefully label and store each separated element. These refined materials, though small in mass, will play critical roles in data storage and audio output. Segment 9. Now, the intricate dance of microfabrication begins. We will grow large, ultra-pure silicon crystals using techniques like the Czochralski process. A seed crystal is dipped into molten silicon and slowly pulled upwards, forming a cylindrical ingot. This requires precise temperature control and a dust-free environment. This seemingly magical process transforms raw earth into the very fabric of our digital logic. Segment 10. These silicon ingots are then sliced into thin wafers, the canvas upon which our integrated circuits will be etched. The surfaces of these wafers must be polished to an atomic smoothness. This meticulous process ensures the flawless creation of the microscopic structures that will define our computer's processing power. Each wafer holds the potential for countless transistors. Segment 11. Photolithography, a process akin to microscopic stenciling, is used to pattern the silicon wafers. A light-sensitive material photoresist is applied, and a mask containing the circuit design is projected onto it. Where the light hits, the photoresist becomes soluble and is washed away, leaving the circuit pattern exposed. This delicate process requires extreme precision and cleanliness. Segment 12. Etching follows photolithography, where chemicals or plasma are used to remove the exposed silicon, creating the intricate pathways and components of the transistors. Different etching techniques are used for different materials and layers. This is where the design of our central processing unit CPU and memory chips physically manifests on the silicon wafer. Segment 13. Ion implantation is used to introduce dopant atoms like phosphorus or boron into specific regions of the silicon wafer, altering its electrical conductivity and creating the transistor switching behavior. This process requires precise control over the type and concentration of dopants. The fundamental building blocks of our digital logic are now being formed at the atomic level. Segment 14. Layers of conductive materials like our refined copper and aluminum and insulating materials are deposited onto the wafer, creating the interconnections between the transistors. These layers are also patterned using photolithography and etching. This multi-layered structure allows for the complex flow of electrical signals within the integrated circuit. Segment 15. Finally, the silicon wafer is diced into individual chips, each containing millions or even billions of transistors. These delicate chips are then packaged to protect them and provide electrical connections to the outside world. Our CPU and memory modules, born from the earth and shaped by human ingenuity, are now ready for assembly. Segment 16. Our refined copper is now drawn into thin wires, the nervous system of our computer. This process involves pulling the copper through a series of progressively smaller dies. The resulting wires will carry power and data signals between the various components. Insulating materials, perhaps derived from natural rubber or processed plant fibers, will be applied to prevent short circuits. Segment 17. The refined aluminum is shaped into the computer's chassis, providing structural support and shielding from electromagnetic interference. This might involve casting, machining, or folding the metal. Consider incorporating natural ventilation designs to aid in cooling. The chassis will be the skeleton that holds our digital creation together. Segment 18. The rare earth elements are crucial for the magnets in our hard drive. Neodymium magnets, in particular, are incredibly strong. These magnets will be carefully shaped and integrated into the hard drive's read, write heads and spindle motor, enabling data storage and retrieval on magnetic platters which themselves require careful material science, perhaps using iron oxide coatings. Segment 19. For the display, we need to create a liquid crystal display LCD or perhaps explore more rudimentary technologies like cathode ray tubes requiring further mining for elements like phosphorus. Building an LCD from scratch involves creating polarized glass, liquid crystal materials, complex organic compounds, and thin film transistors to control individual pixels. This is a significant undertaking. Segment 20. The keyboard and mouse require switches and sensors. These can be fashioned using conductive materials and simple mechanical designs. Consider using natural materials like wood or bone for the housings. The input devices, though seemingly simple, are vital for interacting with our digital creation. Segment 21. Now, the assembly begins. The CPU and memory modules are carefully mounted onto a circuit board, which can be constructed from layers of insulating material, perhaps treated wood or resin-impregnated fabric with etched copper traces acting as electrical pathways. Soldering, using a conductive alloy, perhaps a tin lead mixture derived from mine ores, creates the electrical connections. Segment 22. The hard drive. Graphics card if we are ambitious, requiring more silicon processing. Sound card utilizing our rare earth magnets in the speakers, and other peripherals are connected to the motherboard via various interfaces. These connectors might involve more refined metals and plastics, perhaps derived from processed plant oils. Segment 23. The power supply, crucial for delivering electricity to all components, requires transformers using iron cores and other elements to mine, capacitors, and rectifiers. These components can be painstakingly constructed from raw materials, requiring knowledge of electrical engineering principles. Segment 24. Finally, the assembled components are carefully placed within the aluminum chassis. Wires are routed and connected, ensuring proper airflow and preventing interference. The display, keyboard, and mouse are connected externally. Our computer, born from the earth and painstakingly crafted, is nearing completion. Segment 25. The final step is the software. Without an operating system and applications, our magnificent hardware is just inert metal and silicon. This requires writing code, perhaps starting with a very basic bootloader in assembly language. Consider using natural materials like etched stone tablets or treated animal hides to store the initial program. This is the final, intellectual leap in our creation. Segment 26, powering on our creation, will be a moment of profound significance. If all has been done correctly, a flicker of light, the whirring of a fan, or the faint hum of electricity will signal the awakening of our digital consciousness, born from the very elements of the earth. This journey, from raw to a functioning computer, is a testament to human ingenuity and the fundamental interconnectedness of technology and the natural world.